Okay, class, today we're going to cover sections 1.7 and 2.1. Now remember, class, after you cover section 1.7, you will be ready to complete the first project for this course. The first project actually covers sections 1.1 through 1.7. So as of today, you should be able to look back and be able to go over the project that will be due. I believe it's September 26th. Okay, so now actually we need to go to page 107, not 105. Have to take a quick look at the donuts. Okay, now it's called portion control. Our learning objectives is to describe what apportionment is and why it's used, to compute standard divisors and quotas, to apportion items using a variety of methods. Okay, so now what I want to do, because a lot of this you can read at your leisure, um, I'll read the bottom here because I believe this is important and then it's also historical as well. It says the most common example of apportionment, and as we'll see where the study came from in the first place, is the United States Congress. There are 100 senators in 50 states, 2 senators per state, easy. But in the House of Representatives, the number of representatives is based on the population of the state. There are 435 seats in the House, and they're divided according to population. For example, Florida has 25 seats, Pennsylvania has 19, and Rhode Island has just 2. So why can't we just divide 435 by the population to find out how many representatives per person, then multiply by the state's population? Now, I would tell you this, he makes a very bad joke here. So I would just say this here. The population doesn't evenly go into 435. 435 doesn't go evenly into the population. So you will have some representatives that will be decimals, and you cannot have zero point 0.4 of a person or zero point 0.2 of a person. So that was the need for apportionment here. Apportionment is the process of fairly assigning identical indivisible objects among individuals entitled to shares that may be unequal. We just pointed out that the most logical way to attack dividing up the seats in Congress would be to divide the entire population by the number of seats. This would tell us how many people on average would be represented by one congressperson. This number is known as the standard divisor, and it plays a really important role in apportionment. So we'll highlight the formula next, but don't think about memorizing it. Think about what it means, and you will have a much better chance of understanding this lesson. Throughout this lesson, we'll refer to the objects being assigned as seats, like seats in Congress. The individuals they're allocated to will be called districts. Okay, at the top here, we have the formula for the standard divisor. Okay, class, with the standard divisor, basically we have the total population divided by the number of seats. Okay, so it says here the standard divisor for an apportionment process is the average number of people per seat. So it says here's the apportionment problem we'll be working on in this lesson. A large city has 20 seats to be allocated proportionally among 5 districts according to the population of each district. The populations of the districts in thousands are shown in the table. Number 1, explain why it wouldn't be fair to just assign 4 representatives to each district. Okay, first of all, some of the districts have a significant population than other districts. For example, I'll just put IE. For example, when you compare District 2 to District 5. If you look at District 2 has 4 times the
Third
population that District 5 does. So that wouldn't be fair that we get
page
the
of the
same amount of
lesson.
representation. You said what, Ms. Flores?
I'm trying to mute because my computer's messed up. I keep getting kicked out.
Okay, I'll mute you. Okay, you're muted now. Okay, number 2. It says find the standard divisor for this apportionment and briefly describe what it means. Okay, so again, I'm going to abbreviate standard divisor, and we're going to have the total population. I'll abbreviate that, divided by the number of seats. Now I know some of you only know this symbol as a hashtag, but when I grew up, this was the number sign, so I'm aging myself here. So the total population, notice here the total is 240. So, and remember, this is in thousands. So the total population would be 240,000 divided by the number of seats. We were told earlier that it's 20 seats. So we divide by 20. 240,000 divided by 20 is 12,000. So it'd be 12,000 people per seat. It's 12,000 people per seat. Now, just to let you all know, because some people still don't have their course facts yet, this problem.
You are now muted.
Okay, class. We look here at problem number 3. It says, notice that District 2 has exactly 1/3 of the population. It would seem perfectly reasonable then for that district to get 1/3 of the seats. Why won't District 2 get exactly 1/3 of the seats? Now, if you look at District 2 has 80,000. 80,000 people, and it's 240,000 in the total population, which is 1/3. Now, so basically, 80,000 District 2 is 1/3 of the seats. So if you take 20 and divide it by 3, that would actually give us like about 6.6 repeating. The reason why they cannot get 1/3 of the seats is because you cannot have 0.6 of a seat. That's why they cannot have 1/3 of the seat. So you could put, you cannot have a decimal seat. You cannot have a decimal seat. Okay, now we move on to the next page. Now we have what is called the standard divisor. We have a long definition here of the standard divisor, but what I would like for us to do is to go on to the next page because they're basically telling you how they derive the formula. But on the back here, right here in the middle, it shows you the formula for the standard quota. It's the population of the district divided by the standard divisor. So we look here at problem number 4. It says perform the calculation in part B of the solved example for District 3 in our example problem. Then write a description of what the result of the calculation tells you. Okay, if we look here at B, we end up with the population of the district divided by the total population. Let's write that down. Population of the district divided by the total population times the total number of seats. We could just say times the seats. Okay, now it's basically telling you To summarize the formula for question 4, which is the percentage of the total population that lives in a given district multiplied by the total number of seats, is the theoretical number of seats that each district would get if it were possible.
You are now.
Okay, we call this number the standard quota. So basically this formula is showing you how we will go about getting the standard quota as far as the percentage with the seats. So it says here for number 5, it says find the standard quota for each district in the city described on page 108. Okay. Now with number 4, there was one thing that I did not do. We had the population of the district because they wanted us to do District 3. So coming back here, I wish we would have had the table on that same page. So let me see if I could get the table here. Okay, District 3 is 41,000. So the population of the district is 41,000. The total population we know is 240,000. And then we will multiply it by the number of seats, which is 20. Okay, so now, when we put this in our calculator, we will have 41,000 divided by 240,000. And then we're supposed to multiply this by 20. So this would be approximately 3.42. All right. And then they tell us to write a description here. So this district is supposed to get, this district is supposed to get 3.42 seats. And we know that's not possible. So now, when we go down here, they want us to do the standard quota for all of the rest of the districts. So what I'm going to do, I'm going to list each district here, and then I'm going to write out what they have. So we had a population of the district. So District 1's population is 32,000. And then we divided by the standard divisor. The standard divisor was 12,000. We determined that back in problem number 2, just to show you here. So that was 12,000. And we're going to round all of these to 2 decimal places. District 2 was 80,000 divided by 12,000. District 3 is 41,000 divided by 12,000. District 4 is 67,000 divided by 12,000. And District 5 is 20,000 divided by 12,000. Okay, so now we will put all these in the calculator. So we have 32,000 divided by 12,000, which would give us approximately 2.67. And then we would do 80,000 divided by 12,000, which would be 6.67. And then we would have 41,000 divided by 12,000, which would be 3.42, which is basically what we got back in problem number 4. So we know we're doing the correct thing here. So now we have 67,000 divided by 12,000. So that'd be 5.58. And then finally, we would have 20,000 divided by 12,000. So it'd be 1.67. Okay, so now those are all the standard quotas for districts 1 through 5. Did you all have any questions? Any questions?
Yeah, I have a question. So I want to make sure I have this right. So the standard divisor is going to be total population divided by number of seats.
Right.
And then the standard quota is the population of the district divided by standard divisor.
That is correct.
Okay.
Okay.
Thank you.
No problem. Okay, now we move on to the next page. It says, now that we know how to almost find the number of seats that should go to each district, aside from the pesky issue of fractional parts, the rest of the study of apportionment is about deciding if each district's number of seats should come from rounding its standard quota up to the next bigger whole number or down to the next smaller whole number. Seriously, that's pretty much it. A logical place to start is by simply using familiar rounding rules. So let's give that a try. So number 6, it says round each of the standard quotas you calculated in question 5 to the nearest whole number. Then add the result and explain why that won't work as the number of seats assigned to each district. Okay, so let me just write down the districts here. And then I'm going to write down what their approximations were. Okay, these were all of the standard quotas that we got. Now they're asking us to round the standard quotas. So this is around the 3, this around the 7, this around the 3, this around the 6, and this around the 2. So now we have to add. We add 3 plus 7 plus 3 plus 6 plus 2. So then this will give us 21. So now the problem here is we have too many seats. So it says here that question 6 shows that simply rounding each standard quotient to the nearest whole number isn't a reliable method of apportionment. This realization dates back to at least 1790, when both Alexander Hamilton, the first Secretary of the Treasury, and Thomas Jefferson, hopefully you know who he was, suggested methods for apportioning congressional seats after our nation's first official census. The methods of apportionment that we'll study are all based on first calculating the standard quota, then deciding whether to round up or down. For any district, the lower quota is the result of rounding the standard quota down to the next lower whole number. The upper quota is the result of rounding up to the next larger whole number. Okay, now for number 7, it says use your results from question 5 to fill in the table below for each district. Okay, so now we need to write out our standard quota, which is 2.67 for District 1, 6.67, and so on. Okay, these are the standard quotas for all of these districts here. Okay, now, did everyone understand when I read how you will find the lower and upper quota? Does everyone understand how to find the upper and lower quota?
Isn't it determined on by rounding?
Yes, it is.
So the lower quota would be if you're rounding down, and the upper quota would be if you're rounding up.
Right. But I would tell you this because I don't understand the rounding down thing. So I think this method that I'm about to tell you all, I think would be a lot easier. So for the lower quota, whatever number is in front of the decimal is the lower quota. So this would be 2, 6, 3, 5, and 1. Do you all follow that? Okay, now the upper quota, you just add 1 to the lower quota. So this would be 3, 7, 4, 6, and 2. Do you all follow how to do the lower quota and the upper quota? Okay.
That made it pretty simple. You simplified it. That was good.
Well, thank God. Okay. All right. Number 7. Okay. So we have this here. Now we filled in the table. Now we're going to go over basically to the next page. And we're going to talk about some apportionment methods here. It says the first method we'll study is Hamilton's method, which was approved by Congress for use in 1791, but was never actually used since President Washington vetoed the bill that introduced it. Okay, number 1, assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. Now, if we look over here, when we add the lower quota, this is 11, this is 17. So we know the lower quota here is 17, so it doesn't work. So we have to go over here to number 2. If it does not, assign extra seats one by one to the districts in descending order of size of the fractional parts and their standard quota. For example, if 3 districts have standard quotas 2.93, 4.70, and 3.15, the first extra seat will go to the district with fractional part 0.93, and the second extra seat will go to the district with fractional part 0.70. Okay, we're going to get into that with this problem here. Use Hamilton's method to apportion the seats for the city described in the class portion of this lesson. In completing the table in question 7, you've done most of the work already. Cool. Make sure you clearly write out how many seats each district gets. A table wouldn't be the worst idea ever. Now, I'll admit, this is one of my pet peeves with the book. I just wish they would have provided us with a table, because that would make everything go a little faster. But let me go ahead and do a table. So we'll do a district. I just put D for the district. And then we have 1, 2, 3, 4, and then 5. And then we will have the standard quota. Now the standard quota is 2.67, 6.67, 3.42, 5.58, and then 1.67. Now we know our lower quota because we're going to need that. Our lower quota was 2, 6, 3, 5, and 1. Our upper quota will be 3, 7, 4, 6, and 2. Okay, now, according to this, we would go to, we will put down seats here, because this will be our final answer. All right. Now, according to Hamilton's method, we know the lower quota does not work. Now, what we have to do is decide how many extra seats we need. With the lower quota, this ends up being 17. So that means we need 3 extra seats. So since we need 3 extra seats, we need to go back up to the standard quota. We don't need to look in front of the decimal. We look behind the decimal. We try and find the 3 highest values behind the decimal to assign the extra seats. And if you notice here behind the decimal, we got 67, 42, and 58. We have 3 values at 67 that's larger than all the rest. So for each value that has the 67, we would circle the upper quota. Okay, now, what this means is this particular district where we circle the number gets the upper quota value. The districts that we didn't circle the numbers for, we get the lower quota value. So this would be 3, 7. For District 3, we'd do the lower quota. District 4, we would do the lower quota. And then District 5, we would do the upper quota. So when we add all of these up, 3 plus 7 plus 3 plus 5 plus 2, it equals 20. So we have our 20 seats. Now, are there any questions on Hamilton's method? Any questions on Hamilton's method?
How did you figure out what to circle?
Okay, when you find out first that how many seats that you have that you need, remember we need 20 seats, right? The lower quota gave us 17 seats, so that means we had 3 more seats we need. Okay, you follow that?
Yeah.
Okay,
Yeah.
so once you find out how many seats you need, you go and look back at the standard quota, and then you find, you look behind the decimal, and you find however many seats you need, you find the highest amount, like in this case, it was 3. So we had to find the 3 highest amounts behind the decimal, which happens to be District 1 with 67, District 2 with 67, and District 5 with 67. Do you follow that?
Yeah, I got it.
Okay, now once you do that, all of those with the highest number, you take their upper quota. All the ones that's left, you take their lower quota.
Okay.
I have kind of a situational question.
Okay.
What if, let's say the problem was saying, let's say you still had 3 extra seats, so it was all set up the same way. Or no, there were only 2 extra seats. So let's say the lower quota equaled 18, but you still had the 3 values of the 67 after the decimal. What would you do?
Okay, that is a good, excellent question, and that has not been addressed.
Oh, okay. Okay.
So I'll just be honest with you because that has not been addressed. They did
Okay.
not. They have not even mentioned that in any of these directions. So
Yeah,
I'm
Okay.
assuming that has never happened before. But if we have that situation happen, please show it to me, and we will send it to the editor and all of those. We can't send it to Alexander Hamilton because
Okay. Thank you.
send it to the author and find that out. I'll try and look it up on the internet and see if they may have come across that problem before. But in the time I've done this, I haven't come across that issue before. But maybe Miss Stewart has.
Nope, I was going to say that was a good question because, but it's also kind of a hint that you're not going to have to worry about that either because neither one of us has ever seen that. So, yeah, that's a good question though.
Oh yeah.
They all had 0.6666. So the different, they're all the same too. It's not like you could go up one more decimal.
Right. Unless
Yeah.
you start looking in front of the decimal, I guess that would probably be the tiebreaker, I guess. But then you may run into a problem that they could all have the same population.
That's right.
Yeah.
Yeah.
So I guess that wasn't addressed. Maybe that's why Washington vetoed it. That problem. Maybe. Okay, now the apportionment method that was adopted by Congress after Washington's veto in 1792 was designed by Thomas Jefferson, and it's called the Jefferson's method. It's a bit more complicated than Hamilton's method. It uses what we call a modified divisor. The idea is to make sure that every district gets its lower quota. We know that won't work in general because usually the number of seats will add up to something less than the correct total. And Jefferson's method will make the quotas get bigger by making the standard divisor lower. Remember, the standard quota comes from dividing a district's population by the standard divisor. So if the divisor gets smaller, the quota gets bigger. Okay, just to illustrate this, just throw this here. Let's say we took 100 and divided it by 2. That gave us 50, right? But let's say we take this same 100 and divided it by 20. Do you notice as your denominator gets larger, your end value gets smaller? And then when your denominator gets smaller, the value, your final answer actually gets larger. So that's what they're basically saying here. So if you need more seats, you're going to have to make the divisor smaller. If you need less seats, you have to make the divisor bigger. That's all they're saying. Okay, now Jefferson's method. Assign each district the number of seats according to its lower quota. If this adds to the right number of seats, you're done. Number 2, if the sum of the lower quotas is less than the number of seats, choose a modified divisor that is less than the standard divisor and recalculate the lower quotas. Use this as the apportionment if the lower quotas now add up to the total number of seats. If not, adjust the modified divisor and try again. Okay, so it says Jefferson's method ends up being a trial and error process. We keep trying different divisors until the lower quotas add up to the right total. Let's give it a shot. Recall that the standard divisor calculated earlier was 12. Fill in the following table. Now, first of all, we know 12 actually means 12,000. In each case, getting a modified quota from dividing a district's population by the modified divisor 11. So, what they want us to do, and remember this 11 is 11,000. They want us to take each one of these and divide it by the 11,000. Now, I'm not going to write this out. I'm going to put it on the calculator. And as a matter of fact, since I have all these values here, I would just change them to 11,000. That's one thing I like about Desmos. Just go back and just change one number and don't have to retype all of them over again. Now, we go back here. So District 1 would be 2.91. District 2 would be 7.27. District 3 would be 3.73. District 4 would be 6.09. And finally, District 5 will be 1.82. Now they asked us to take the modified lower quota. We still just take the number in front of the decimal. So we add 2, 7, 3, 6, and 1. So now we add this up. This will give us 19. So it says add up the modified lower quotas. Does this apportionment work? It'll be no. It only gives us 19 seats, and we need 20 seats. Okay, so now that means we're going to have to try this all over again. Our next attempt will be to change the divisor we're using. Do you think we should make it bigger or smaller? Why? Do you think we should make it bigger or smaller? And why? Anybody?
Smaller?
Yes, it'll be smaller, but why?
Because when you, I forgot how to word it, but when you make that smaller than the, I don't know how to word it.
Okay.
I forgot.
Smaller because we need an extra seat. If we needed to go down, and a word you were looking for is denominator. If we need to go down, then that means we would have made the denominator larger. But since we need an extra seat, we need to make it smaller. Okay, number 5. It says try again with modified divisor 10.5. Does the apportionment work now? Is it the same as the one we got from Hamilton's method? Okay, so So we'll try 10.5. Now we know 10.5 is really 10,500. So we'll
I have a
go
quick
here.
question.
Yeah.
I'm sorry, I have a quick question. Before we move on, I'm confused as to why I'm a little hung up as to why we like making it smaller, like making the denominator smaller makes it bigger.
Oh, you're wondering why that happens?
Yeah, I'm confused.
Oh, okay, okay. Hold on, let me finish changing these to 10.5 and then I will answer your question. Okay. All right. Let me ask you a question. Have you ever had to, okay, you ever used to watch those old crime stories where you would have like 3 people rob a bank and then 2 of them get off to the side and say, okay, let's get rid of the third person because we'll get more if we just divide it by 2 instead of 3?
Okay.
Okay. Because the smaller amount you have to divide, the more you would get. Just like taking a pizza. You know, a pizza, let's say it got 10 slices. You got 5 people. That means everybody only get 2 slices, right? Right?
Right.
Okay. But then let's take that same pizza and say it's only 2 of y'all. Now you both would get 5 slices apiece, right?
Okay, I get it. I
Right.
got hung up for a second. It's making sense.
Okay. Okay.
Thank
Good.
you.
No problem. Okay. So we go back here. The modified quota here for District 1 would be 3.05. District 2 would be 7.62. District 3 would be 3.90. District 4 would be 6.38. And finally, District 5 would be 1.90. Now, if we go to modified lower quota, it's just the number in front of the decimal. And then when we add this up, this now gives us 20. It gives us 20 seats. Now, it says here, does the apportionment work? We could say yes, it works. And then it says, is it the same? Is it the same as the one we got from Hamilton's method? And you could say no. And if we go back to Hamilton's method, see, can I compare these side by side? No, I cannot. Let me do it like this here. No, that won't work. All right. Okay. The districts that's different, it looks like District 4 and 5 are the only ones that's different. If you look at District 4 and 5 from Hamilton's method, you notice that District 4 has 5 and District 5 has 2. But when we get to Jefferson's method, District 4 has 6 and District 5 has 1. So you could say no, District 4 and 5 are different. Okay. Now it says Jefferson method was used in Congress until 1842, when it was replaced with the new method devised by Daniel Webster, a distinguished congressman, senator, and 2-time Secretary of State. Webster's method also uses modified divisors, but is based on standard rules of rounding rather than lower quotas. Okay, number 1, assign each district the number of seats by using standard rounding rules on the standard quota, rounding up if the fractional part is 0.5 or greater, and down if the fractional part is less than 0.5. If the sum of the seats is equal to the number of seats available, use this as the apportionment. If not, modify the divisor and try again. If there are too many seats assigned, use a larger divisor. So basically, what Webster's method does, first thing you do is regular rounding. Then if that doesn't work, then you're going to modify your divisor like we just did in Jefferson's method. You modify your divisor and then you round again until you come up with the proper amount of seats. So let's go through and try this. So first of all, we already know from question 6 in the class portion that using standard rounding rules won't work for the apportionment problem we've been studying. That resulted in 21 seats. So that means we had too many seats. So we could skip right to step 2 in Webster's method. Since we had too many seats, we should try a larger divisor. Just like we did with the pizza example, the more people it is, the less that you would get. So since we want less seats, we need to adjust this divisor. So it says use a modified divisor of 12.5. So we're going to go here and change these divisors to 12,500. Right.
What in the world is this?
Okay. Okay, so now we put in 12,500 for each one of these. So now we have our modified quota. So this would be 2.56. This would be 6.4. This would be 3.28. This would be 5.36. And then finally, this would be 1.6. Now, they want modified rounded quota. So this would be 3, 6, 3, 5, and 2. And when we add all this together, this will equal 19. So we used a little bit of too high of a number. So we're going to go down a little bit. Let's try, instead of 12.5, let's try 12.2. Since we need to go down one seat, let's go to 12.2. So that'd be 12,200. All right. So if we go back here, I have to draw another table here. District 1, 2, 3, 4, and 5. Then I'll put MQ for modified quota, and then MRQ for modified rounded quota. So the modified quota here for District 1 would be 2.62. For District 2, it'll be 6.55. District 3, it'll be 3.36. District 4, it'll be 5.49. And finally, District 5 will be 1.64. Now we round these. This would be 3, 7, 3, 5, and 2. Now when we add all these together, it turns out that it gives us the right amount of seats. So this is basically it. This would be the seats that we would have here. So we can do another column and we could just put seats to let us know exactly how many seats each district gets. Any questions? Okay. Now, we move on here to the back. Now, I'm not going to read the whole section of the back, but if we start here at number 8, they're basically asking us to determine which of these situations would need to be apportionment and which ones would not. So number 8, it says a school district raises an extra $1.2 million when a levy passes and decides to divide it among all of the schools in the system based on enrollment. Okay, this is not apportionment because money can be divided evenly. Okay, number 9. A manufacturing company with 4 locations buys 22 new stamping machines. The plan is to divide them among the locations based on production levels over the last 4 years. So if you look here at 22, we know 4 does not go evenly into 22 for the 4 locations. So this would be apportionment. And that is because you cannot have a fractional machine. Because I mean, each one of these could give what about a half of a machine. So each one could what get 5.5 machines. So we know half of a machine would do no good. So we would need apportionment. Okay, number 10. Each day, a team of engineers that works for a utility company decides how to allocate power on the grid to various neighborhoods based on past usage statistics. This is not apportionment because electricity can be divided evenly. Okay, now number 11. It says each day the manager of a large roofing company decides how to allocate workers to that day's jobs based on the size of the job and the time of completion. So basically, this would be apportionment because we cannot have a fractional person. For example, if it's 22 jobs and it's 4 people, you cannot send half a person on each job. So that's why that is apportionment as well. Okay, now